Hello, class! Today we're going to learn about Newton's law of motion. Before we begin discussing Newton's three laws, we must first understand the concept of force. Force is basically a push or a pull acted on an object. An object at rest needs a force to get it moving or change its velocity. Other forces other than push or pull could be weight, tension, friction, spring, and centripetal force. In this screencast, we'll only discuss the forces caused by push, pull, and weight today. Newton's first law states that any object at rest or moving at a constant velocity in a straight line will continue at that state until a non-zero net force acts upon it. The non-zero net force is included in the first law because two equal forces acting on an object in such a way could change its velocity. So the object could still be at rest or still moving at a constant velocity. The term inertia means resistance to movement. An object won't change its state unless a non-zero force acts upon it. Before we continue with Newton's second law, we must understand the definition of mass. A basic definition of mass is the amount of stuff in an object. Mass is not the same as weight. Weight is a force that accounts for gravity. So the weight of an object on Earth will be different than on the Moon, whereas mass will always be the same, no matter if the object is on Earth or out in space, because it's the quantity of the atoms inside the object. Recall that inertia means resistance towards movement. Well, if you think about it, mass measures the inertia for an object. The greater that mass of an object, the harder it will be to push an object because there's more resistance due to the larger mass. Thus, greater the inertia means greater the mass of an object. The SI unit for mass is kilograms. Alright, now that we understand mass, we can continue on with Newton's second law. The second law is essentially the equation of the sum of the forces equals mass times acceleration. In Newton's words, to describe this equation, is acceleration is proportional to force and inversely proportional to mass. That sum symbol you see in front of force is important to include because there could be more than one force acting on an object or a system. Thus, we must add all the forces acting on the object or system to have it equal its acceleration times mass. If you notice on the previous slide, force is a vector, just like acceleration is a vector. So that means force has the magnitude and direction. The unit we use for force is named after Newton. We use the letter capital N to indicate the unit Newton. So instead of writing kilograms times meters per second squared, we can just write the letter N. Thus, the unit Newton equals kilograms times meters per second squared. Now on to Newton's third law. Any force exerted on an object has an equal and opposite reaction. So if you punch a wall, the force you put into the wall will be the same force the wall exerts on your fist, but in the opposite direction. Keep in mind, when you think about the third law, the forces are on different objects, not on the same object. So in this example, shows the force on the wall caused by the skater and the force on the skater caused by the wall. A really cool example of Newton's third law is a rocket launching. The gas exerted out causes a reaction of the rocket to propel upward. Now that we've gone over Newton's three laws, let's learn how to apply Newton's equation of sum of the forces equals mass times acceleration. The first type of force we'll look at is weight. Recall that weight is a force. So let's replace the sum of the forces with either Fg or W. Either variable is fine. And for acceleration, it's due to gravity, so let's replace A with G. Hopefully this equation makes it clear why mass is not equal to weight. Now, according to Newton's third law, every action has an opposite and equal reaction. Here, we have a force, weight, acting on a surface. The surface gives a reaction equal to the weight, but in opposite direction. We call this force caused by the table the normal force. We define the normal force always perpendicular to the surface. The variable we could use could be either f of n or just the letter n. The arrow you see drawn on Mr. Lincoln is a rough sketch of what we call a free body diagram. We'll further discuss how to draw a free body diagram during class. For now, here's a brief overview of how free body diagrams are applied to solve problems. The first step with a force problem is to establish a coordinate system and sketch the force vectors applied on the object. The next step is to calculate each force components in the x and y direction. If appropriate, Newton's equation can therefore be applied to each direction separately. This particular problem is a basic vector problem of solving for the resultant force. In class, we'll learn how to use Newton's equation with the help of a free body diagram.